Hello everyone. On this video we will be going over vector valued functions and space curves. Okay, so starting off, if you think back, okay, a curve on a plane or plane curve is a set of ordered pairs f of t and g of t. Remember, we're talking about parametric equations, so those are the curves on a two-dimensional plane. Together with their defining parametric equations, and that's x equals f of t and y equals g of t. Okay, so that's just a curve on a plane. Now a space curve is of course in three dimensions. And that space curve, we'll call it uppercase C, is the set of all ordered triples. And that's f of t, g of t, and h of t, together with their defining parametric equations. Okay, and those parametric equations are x equals f of t, or some function of t, y equals g of t, and z equals h of t. And that's where f, g, and h, give that a little more space, there we go, are continuous functions on the interval, on the t interval. On an interval that we will call I. All right. Okay, which leads us to our actual definition of a vector valued function. Definition of a vector valued function. Okay, so in other words, a function in the form that we have listed up there. So it's in the form that we'll call R of t, or you may see V of t, W of t. We just happen to pick our vector of t. Is equal to f of t times the I unit vector plus g of t times the j unit vector. And again, that's the xy plane, or two dimensions. Or our R vector of t is equal to f of t times the I unit vector plus g of t times the j unit vector plus h of t times the k unit vector. Okay, and of course that's in 3D space. Okay, so whether two dimensions or three, it doesn't matter. It's the Same setup, just one extra term. Okay, so it is a vector. Well, vector valued function, to be more precise, where the component function that will call those, so f of t, g of t, and h of t are your component functions. Okay, and those are real valued functions. With t as your parameter, of course. With a parameter t. All right. Okay, so if you are still writing, feel free to press pause, but we're going to go ahead and continue on our next page. Okay, so to kind of give you a visual description, let's say if we draw our two-dimensional XY axis, we have our X and we have our Y, and we draw our three-dimensional axis. So we have our X, our Y, and our Z right up top. Okay, so what if we had a curve that kind of looks like this? Okay, so if we look at our value here, that's our vector t sub 0, or our initial point. Our vector t sub 1, our t sub 2, and it keeps on going till we get to the end. So our vector we'll call t sub n. Okay, so in 3 dimensions, pretty much the same thing. We're just going to track it all the way through, and of course this arrow shows that this is the direction where t increases. Okay, so let's say if we have the vector like this in 3 dimensions. Again, we have our vector t sub 0, our vector t sub 1, our vector t sub 2, and it keeps on going all the way to the end for our vector of t sub 0. Okay, so this is our 2-dimension, and this is our 3-dimensional. All right, and remember, your vector just goes from your origin to each point. All right. Now we're going to look at the limit of a vector valued function. And honestly, it's pretty close to, or almost identical to, the limit of a real valued function, which you learned in Calc 1. Definition of the limit, not a limit, of the limit of a vector valued function. All right. So let's say if our vector is a vector valued function such that, that's my little st, such that r of t equals f of t times the I vector. plus g of t times the j vector, then that means the limit of r of t vector as t approaches a, or some value a, is equal to the limit of each term. So that's the limit of f of t as t approaches a times the I vector, plus the limit of g of t as t approaches a times the j vector. Or, of course, in 3 dimensions, you just have one extra term. So r of t equals f of t times the I vector, plus g of t times the j vector, plus h of t times the k vector. Let me clean that up. There we go. Okay. Now, same thing, then that means the limit of our r of t as t approaches some value a will equal the limit of f of t as t approaches a times the I vector, plus the limit of g of t as t approaches a times the j vector, plus the limit of h of t as t approaches a times the k vector. Okay, now these are true, but we're doing this assuming that the limit actually exists. Okay, so provided f, g, and h have limits as t approaches a. Okay, of course, if there are no limits, then the limit just doesn't exist. Okay, now how do we find the domain of each one? Pretty basic. Unless they tell you a different domain, let me kind of separate that. Unless a different interval is given, the domain of our vector of t is the intersection of the domains for our f of t, g of t, and h of t if we're in 3 dimensions. Oh, I'm about to write the g of t first. So for f of t, g of t, and h of t. Okay, and I'll show you what I mean by that in the example. All right, so if you are still writing, feel free to press pause. But we're going to go ahead and go to our first example. All right, so for example, say if we wanted to find the domain of the vector valued function, well, function, since there are 2 of them. Let's say for problem A, we have r of t is equal to 5t times the I vector minus 4t times the j vector minus 1 over t times the k vector. And let's say for problem B, we have r of t is equal to f of t vector plus g of t vector, where we know our big F of t vector, well, f vector of t, is equal to cosine of t times I vector minus sine of t times j vector plus square root of t times the k vector. And g vector of t is equal to cosine of t times the I vector plus sine of t of our j vector. All right. So let's look at problem A. Let me kind of separate this here. Okay, so problem A. R vector of t equals 5t I vector minus 4t j vector minus 1 over t k vector. Okay, so now your component functions which you don't have to write this down, but it helps you with your terminology to kind of jot little things like this down. Your f of t is equal to 5t. Your g of t is equal to negative 4t. And your h of t equals negative 1 over t. Okay, so now f of t, t is defined for every real number. So from negative infinity to infinity, you plug in t, you'll get a real number answer. So your domain is negative infinity to infinity. Same thing with negative 4t. If you plug in any real number for t, you will get a real number answer. So it's defined for every number. So your domain here is negative infinity to positive infinity. Now for h of t, you notice you have that 1 over t. And if there's one thing we know is that the denominator cannot equal 0. Okay? So that means the domain for h of t is from negative infinity to 0, and then back on the other side of 0 to positive infinity. So basically any number except 0. When you get to 0, it has to skip to the other side and keep on going. Okay. Now, we know that all three of these can't have the domain of negative infinity to infinity, all because of this last one. The only domain that works for all three is this very last one. So whatever domain works for all three is the domain we have to pick. That means your domain of r of t is negative infinity to 0 and 0 to infinity. All right, so let's start with problem B. Okay, so for problem B, we have, as a matter of fact, before I get started, just an idea. I want you to start on this one. Okay, so what I want you to do is go ahead and press pause and see if you can do problem B on your own. All right, so assuming you've pressed pause and worked this one out, let's go ahead and verify your answer. So f of t plus g of t Okay, so really we know this is just cosine of t times the I vector minus sine of t times the j vector plus square root of t times the k vector. Plus cosine of t times the I vector plus sine of t times the j vector. Okay, so we can see here that this plus sine of t and minus sine of t, they cancel each other out. Okay, so we have cosine of ti, cosine of ti. So really that gives us 2 cosine of t times the I vector plus square root of t times the k vector as our r of t. So really this is equal to your r of t. Clean up that equal sign a little bit. There we go. Okay, so we can see here, because it's next to your I vector, this is your f of t. Okay, so we know that f of t equals 2 cosine of t has a domain of negative infinity to infinity. Okay. Now this isn't our g of t, because remember g of t is next to your j vector. Our j vectors cancel out, so this is your h of t. H of t equals square root of t has a domain of 0 to positive infinity. Okay, remember, square root can be negative, or you're diving into complex numbers, and we're dealing specifically with real numbers. Okay, so out of both of these, the only one that's defined for all of them would be from 0 to infinity. So the domain of r vector of t is 0 to infinity. All right, so that is your domain for the entire vector. Okay, so if you are still writing, feel free to press pause, but we're going to go ahead and go to our next example. All right, so for example, what if we want to evaluate and simplify vector valued functions at the indicated value of t? If possible. All right, and our vector valued function is r of t equals 1/2 t squared times your I vector minus t minus 1 times your j vector. Okay, so for problem A, we want to evaluate our vector of 1, B, our vector of 0, C, our vector of s plus 1, and I'll put a line through my s because when I write fast, my s tends to look like a 5, and D, have r of 2 plus theta t minus r vector of 2. So let's say for, kind of do a little separating here. For problem A, we have our vector of 1, which of course just means we replace all of our t's with 1. So you have 1/2 times 1 squared times the I vector minus 1 times the j vector. Of course, this just becomes 0, so that disappears. So we see that our vector of 1 is just equal to 1/2 I vector. All right, so that's pretty straightforward, just plug and chug. So for problem B, same thing with our vector of 0. Okay, so that's equal to 1/2 0 squared times the I vector minus 0 minus 1 times j vector. This time, that disappears because it's 0. Okay, so we end up with minus -1, which is just plus 1. So our vector of 0 is equal to just 1j, or our j vector. Clean that up. There we go. Okay, so what about problem C? We have r of s plus 1, okay, which is just 1/2 s plus 1 squared times the I vector minus s plus 1 minus 1, s plus 1 minus 1 times the j vector. You don't have to factor out the s plus 1 squared. You can leave it like that. So we have 1/2 s plus 1 squared times the I vector. Plus 1 and minus 1 cancel each other out. So that's just minus s times your j vector. Okay, and now for problem D. Yeah, for problem D, as a matter of fact, I want you to go ahead and press pause and try to do problem D on your own. All right, so assuming you've gone ahead and worked out problem D, let's go ahead and verify your answer. Okay, so our vector is equal to, or not our vector is equal to, let's do 2 plus delta t first. Okay, now that is equal to 1/2. Let me kind of separate that a little bit. 2 plus delta t squared times your I vector minus 2 plus delta t minus 1 times your j vector. Okay, so you have your 2 plus delta t minus 1. Okay, now for this one, we're going to go ahead, forgot to do that. We're going to go ahead and factor that out. Now, we left this one like that, but this one we're going to go ahead and factor out to simplify it. Okay, so we have 1/2. So 2 plus delta t squared will be 4 plus 4 delta t plus delta t squared times your I vector minus 2 plus delta t minus 1 is really just 2 minus 1, which is 1. So 1 plus delta t times your j vector. Okay, so if we go ahead and distribute that 1/2, we will end up with, move that over just a little bit, 2 plus 2 delta t plus 1/2 delta t squared times the I vector minus 1 plus delta t times your j vector. Okay, so that's your r of 2 plus delta t. And I'll put a little check right here. Okay, so we know that r of 2, so our vector of 2 is just 1/2 times 2 squared times the I vector minus 2 minus 1 times the j vector. Okay, so 2 squared is 4. 4 divided by 2 is 2, so we end up with 2 times the I vector. 2 minus 1 is 1, so you have minus 1, so minus the j vector. Okay, so we have our r of 2. Okay, so if we go ahead and subtract these, r vector of 2 plus delta t minus r vector of 2, move that up a little bit, we will end up with 2, well, if we go ahead and distribute the I, we have 2I vector plus 2 delta t times the I vector plus delta t squared times the I vector minus 1 times the j vector minus delta t times the j vector. Oops, that's yet one j. So that will be minus r of 2. So that's, remember, that's minus this whole thing. So minus 2i minus j. So we're going to have to distribute the negative here. So you have minus 2i vector plus your j vector. Okay, so you have plus 2i minus 2i, so those cancel out. You have minus j plus j, so those two cancel out. So we end up with 2 delta t, and we're going to put the i's next to each other, plus delta t squared times your I vector. And so the only j vector left, so that would just be minus delta t times your j vector as your answer. All right. So again, if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next page. Okay. Now, again, the vector valued function have a lot of similar traits to real valued functions. Okay. So if we have the limit of a valued function, okay, we can just apply it the same way that we did before. Okay, so it's nothing really all that different about how we've done it. Okay, so we're going to go ahead and jump right into our examples here. Okay, so for example, what if we wanted to evaluate the limit of, okay, let's say we wanted to evaluate the limit of r of t equals t times the I vector plus t squared minus 4 over t squared minus 2t times your j vector plus 1 over t times your k vector. Now, just like Calc 1, it hasn't changed one bit. We just evaluate the limit at each point, well, at each term. Okay, so you have the limit of t times the I vector. Oh, forgot to put the last part as t approaches 2. There we go. It makes a whole lot more sense. Okay, so limit of r of t as t approaches 2 is equal to the limit of t as t approaches 2 times the I vector plus the limit of t squared minus 4 over t squared minus 2t as t approaches 2 times your j vector plus the limit of 1 over t as t approaches 2, and that's times k vector. Okay. Now with this, let me give it a little more space. I'm going to move this down a little bit. Now with the first term and the last term, you just plug in t equals 2 and you're okay. So the limit of t as t approaches 2 is just 2. So you have 2 times the I vector. And the third term, again, you plug in 2, you have 1/2. So you have 1/2 times your k vector. Now this middle term, you plug in 2, you get 0 over 0, which isn't an answer, but we know it's an interdeterminate, so we can just use L'Hopital's rule. So using L'Hopital's rule, that gives us the limit as t approaches 2. The derivative of t squared minus 4 is 2t over the derivative of t squared minus 2t is 2t minus 2. Okay, where we can go ahead and plug in our 2. Okay, so we have 2 times 2, which is 4, over 2 times 2 is 4, 4 minus 2 is 2, so we have 4 over 2, which is 2. So this gives us 2j. So that means the limit, forgot my little vector symbol, r of t as t approaches 2 is equal to 2i vector plus 2j vector plus 1/2 times the k vector. Okay, so as you can see, it's pretty straightforward, and not a whole lot of difference from Calc 1. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and go to our next example. Okay, what if we wanted to determine the intervals, and clean that up, there we go, where, okay, I'm writing entirely too fast, where the vector valued function the r of t is equal to t times your I vector plus arc sine of your t vector times the j unit vector plus t minus 1 times your k vector is continuous. All right, so just like before, we look at each function of t, and we see where they're continuous. Okay, so for your f of t equal to t, we see that's continuous everywhere. So that's continuous on the interval negative infinity to infinity. Okay, so what about g of t equals arcsine t? Okay, so if you remember your domain from trig, arcsine has a domain of -1 to 1. So it's continuous on the interval -1 to 1. Okay, and of course, t minus 1 is continuous everywhere. All right. So that means the entire thing is only continuous from -1 to 1. All right. So again, it's pretty straightforward. Nothing really jumping out as odd there. All right. So hopefully this video was more of a refresher than anything, and you kind of remember the stuff you did in Calc 1. So that is it, and I'll see you on the next video.